We'll now begin section 5.1, where we'll discuss exponential functions and their graphs. Let's begin with a definition for an exponential function. Let a be a fixed, positive, real number not equal to 1. The exponential function with base a is the function f of x is equal to a to the x. The thing to remember about an exponential function is that your variable, the x, is in the exponent. So an example of an exponential function would be f of x is equal to 2 to the x. A is a fixed, positive, real number, like 2. And your x is part of your variable, or your variable x is part of the exponent. Now, let's discuss the behavior of exponential functions. Given a positive real number a not equal to 1, the function f of x is equal to a to the x. So if we graph this function, it is a decreasing function if the a is between 0 and 1. It is an increasing function if the a is greater than 1. And we'll look at some examples of this in just a second. In either case, the point 0, 1 lies on the graph. The domain is the set of all real numbers, and the range is the set of all positive real numbers. So let's look at two examples where we're going to graph. So first we're going to start with f of x is equal to 3 to the x. So you want to ask yourself, what is playing the role of the a? So in this case, the a is equal to 3. And obviously 3 is greater than 1, so we're dealing with this case. So we expect our function to be an increasing function. And so in order to draw it, we're basically going to set up a table of values. And we're going to select some points that are easy to evaluate. So for example, I'm going to select the point x is equal to 0. If I plug a 0 in for the x, I get 3 to the 0, and I know that anything to the 0 power is equal to 1. I'm also going to select x is equal to 1. If I plug a 1 in for the x, I get 3 to the first, and I know that that's equal to 3. I'm also going to select negative 1. So 3 to the negative 1 power is the same thing as 1 over 3 to the first, which is 1/3. So selecting the 0, the 1, and the negative 1 make plotting the graph easy because your values for f of x are easy to work with numbers. So let's take a quick glance at this graph. We're going to plot these 3 points. All right, we're working on part A right now. So we've got the point 0, 1, we've got the point 1, 3, and we've got the point negative 1, 1/3. We connect our dots in an increasing fashion, and we have our exponential function. And you will find that all exponential functions have this general shape, whether it be increasing or decreasing, as we see in part B. The shape is the same of the graph. Okay, so let's back up. Let's go back to part B, and let's work on this one for just a second. In this case, what is your a value? Your a value is 1/2. So we know that the a value is falling between 0 and 1. And so we expect it to be a decreasing function. And so we're going to do the same thing. We're going to pick the same 3 points. We're going to go with 0, 1, and negative 1. If we put a 0 in for x, anything to the 0 power is equal to 1. If we put a 1 in for x, 1/2 to the first power is 1/2. And if we put a negative 1 in for x, okay, how do we evaluate that? We can look at that as being 1 to the negative 1 over 2 to the negative 1. Remember that if we cross this fraction line, the exponent changes its sign. So we can drop 1 to the negative 1 down, it'll become positive. And we can move 2 to the negative 1 up, and it'll become positive. So we're basically looking at 2 over 1, which is going to be 2. And so we'll plot those 3 points, and we'll take a look at our graph, remembering that it's a decreasing function. Here is our point negative 1, 2, 0, 1, and 1, 1/2. We know it's decreasing, and we know the basic shape of the graph. And so that allows us to graph our exponential function. Now, we're going to look at some variations on these graphs for the exponential function. So we're going to start with 1/2 to the x plus 3. So what you want to keep in mind here is that we're seeing some transformations like we learned about earlier in the semester. So we know that this is based on the graph of 1/2 to the x power, which we just graphed here. This is the graph of 1/2 to the x power. So how is it changing? Because they have replaced the x with an x plus 3. So what's happened is they've come in and they've said, okay, let's take off this x, and in its place, we're going to put x plus 3. So remember, doing that is a left or right shift. If you're replacing the x with x plus a number or x minus a number, then you are shifting horizontally, either left or right. So which way does it go? Remember, it sort of goes the opposite of what you might think. If you have a plus 3, it's going to shift to the left. Okay, so it is this graph shifted to the left 3 units. So let's take a look at what that looks like. All right, so in the green, in the dotted line, you see the original graph. We have taken now each of these points and moved it back 3 units. So 1, 2, 3, there's the first one. Coming across with this one, 1, 2, 3, there's the second one. And then 1, 2, 3, there's the third one. Connecting on the purple graph is the graph of 1/2 raised to the x plus 3. Okay, our next one is the graph g of x is equal to negative 3 to the x plus 1. So we know what the graph of 3 to the x looks like. Okay, that is this one, the first one that we drew over here. This is 3 to the x. So now we just have to consider how that graph is changing. So how does it change when we put a negative in front? What does the negative do? Remember that the negative reflects the graph over the x-axis. And then what effect does the plus 1 have? If we add a plus 1, remember that graph moves the graph up 1 unit. So we have our original graph here. It's now going to be flipped over the x-axis and then moved up 1 unit. So let's take a look at what it's going to look like. All right, so we've got it moved up a unit and flipped over, and we see the purple graph is the graph that we want. All right, and you can see that your points have been reflected and they have been shifted up by 1 unit. All right, and finally, we have the graph h of x is equal to 2 to the negative x. And so this is a new graph for us. We know that this would be based on the graph of 2 to the x. And then we have to consider the fact that the x has been replaced by a negative x. So remember, what does that do? If you come in and you replace this x with a negative x, remember that that causes the graph to reflect over the y-axis. And so let's take a look then at what that graph is going to look like. All right, 2 to the x is the green dotted graph, and you could certainly figure that out based on a couple of key points like we did in the other examples. and then you're going to reflect that graph across the y-axis, all right, to get your new graph. So you can see if this is a point 1, 2, you're going to reflect it over to negative 1, 2. The point at 0, 1 stays the same as it reflects, and this purple point at 1, 1/2 becomes negative 1, 1/2. All right, so your purple graph would be your graph of f of x is equal to 2 to the negative x. So the last thing we want to do in this section, we've talked about what an exponential function is defined as. We've looked at some basic graphs and transformations. The last concept is to solve exponential equations. And so they give us a procedure table in this section with some steps, and we're gonna try to follow these steps as we look at some examples. So it says that the first step is to isolate your exponential. So move the exponential term containing the x to one side of the equation and anything else to the other side. You want to find a base that can be used to rewrite both sides of the equation. And then you want to equate the powers and solve the resulting equation. Now, as always, this is easier seen with an example, so we're going to look at 3 different examples where we can follow this procedure table. So our first example is 25 to the x minus 125 is equal to 0. And we want to solve the equation. So step 1 says to isolate the exponential. So that means that we want the term that has 25 to the x by itself on one side. So in order to do that, I'm going to add 125 to both sides of the equation. That gives me 25 to the x is equal to 125. And that takes care of step 1. Step 2 is to write both sides with the same base. All right, so what that means for us is that we want to try to write both sides with a certain power that have the same base. So for example, the 25 can be written as 5 squared. Now it still has the x on the outside, but the 25 could be replaced with 5 squared. And the 125 could be written as 5 to the third. And then it says to simplify if necessary. And so the only really way to simplify is to say this 2 times x is going to be 5 to the 2x is equal to 5 to the third. And then the third step, once you have with the same base, is to equate the powers. So this means to set the powers or set the exponents equal and solve. So I'm going to take 2x and set it equal to 3 and then solve that. So we solve by dividing by 2, and so our final answer will be 3/2. All right, let's move on to part B. Part B, we have y to the, or 8 to the y minus 1 equals 1/2. We're going to get rid of that right there. Okay. Step 1 is to isolate the exponential. That step is done. The 8 to the y minus 1 is by itself on one side of the equation. Step 2 is to write both sides with the same base. So 8 could be written as 2 to the third. And 1/2 could be written as 2 to the negative 1. All right, part of step 2 is to simplify. So let's go ahead and distribute. So we're going to have 2 to the 3y minus 3 is equal to 2 to the negative 1. And then the last step is to set your exponents equal to each other. Now remember that you can only set your exponents equal to each other once the bases are the same. So they both have to have the 2's in order for you to set your exponents equal to each other. We'll then solve the resulting equation, and we'll end up with a final answer of 2/3. And in part C, we have 2/3 raised to the x power is equal to 9/4. Again, step 1 is done. The exponential is isolated. Step 2 is to write both sides with the same base. So I could leave 2/3 to the x alone because I can't really do anything with the 2 or the 3. I could rewrite the 9 as 3 squared and the 4 as 2 squared. So that would mean that I could have 2/3 to the x. Now, when I look at this, if I'm going to have it have the same base, this is 2/3 and this is 3/2. So it would actually be better if it was the same fraction, if both of them were 2/3. So what if I take this 3/2 and move it down, making the exponent negative, and I take the 2 to the second and move it up, making the exponent negative? Then I could say 2/3 to the x power is equal to 2/3 to the -2 power. And then our bases are alike, and the last step is to set your exponents equal and solve, which is not really necessary at this point. We have our final answer, x is equal to -2.